Right, we begin in this lesson by trying to examine to what extent there is a straight line that represents data, that we've already concluded is correlated linearly. All right, let's break all that down. We've recently seen how you find the value of R using a graphic display calculator, and it'll also be done on a computer using different spreadsheets. So once we have an R value that suggests that a linear relationship, a very near linear relationship exists, how do we go ahead and find the line that represents the trend of that data? And that's what we're going to be doing today. Okay, so let's take a look at that. The first thing you can do, and there's a couple techniques here. One is just, if it's not important that your results are 100% airtight reliable, you can just approximate one by eye, but that doesn't mean it's just a flat out guess. There are some things to do. Here it says, for example, there's no fixed rule, but we suggest that a line at best fit is not appropriate if your R value is under about 0.85 or so. That's because it's not strong enough, the linear relationship or the proposed linear relationship, for a straight line to actually represent the data. It would be a little bit dishonest. So what can you do? Well, there has to be a way to avoid two different people with differing opinions coming up with two different lines of best fit or trend lines. So to minimize the differences between them, there's a couple things that we do. The first thing is you got to calculate of those two different data sets what we call the mean point, or the mean point, I guess technically, because the mean of the X data and the mean of the Y data have to be computed, added to your scatter diagram, and the line of best fit that you propose that represents the data must intersect that point. It's almost like a pivot point. If you had a point down there, which is the mean point, the line you choose would have to be one that it has to go through that. Well, last time I wasn't drawn very well. Has to go through that point. Now, so if I take a look at our, recurring example about the young athlete discus throwers, I'll go ahead and put that graph back in here. What I could do is go and find out the mean point, or the average age and the average distance thrown, and add that to our series of data in here. And from there, you can see that the mean of the ages is 15 and the average distance thrown is 29. So I went ahead and put a big red dot on the scatter plot that's consistent with that point. And now what I'm going to do is I'm going to find a straight line that goes through that point and captures the essence or the direction of the data. I'm trying to keep about half of it above and half of it below. No two people are going to likely have the exact same line, but they'll all be pretty close, especially if they include that mean point. Now, I know we've had this discussion before, but I just want to go back again and don't want anyone to miss this. There's the line at best fit is typically used to understand what's happening at places where data doesn't itself exist. Like it's trying to explain what's happening at, in the gaps here or all over the place. If you are trying to use the line to work out what's happening between the lowest and highest point in a data set, that's called interpolation. I suppose focus on the word in or inside. If you are then trying to approximate or do a best guess of what's happening way off in the distance, either before or after the data set, that's called extrapolation, and that's where we can get into some dangerous territory. That's like, the 112-year-old grandmother throwing the discus farther than anyone else. It's highly unlikely. So these models that we're going to be making, these lines of best fit, they typically have a short period of validity, and then they are less accurate. So, can you read that? Accuracy of the extrapolation depends not only on how well it fits the model, but also the assumption that the trend will continue, and that's the case. And oftentimes, it's not reasonable to assume that a trend will continue, but in some cases, it is, and that's a defense that you would have to make if you're going to go ahead and do that. Here's again with the discus throw. They're estimating that a person who's 50 years old, based on that line of best fit, would throw it over 150 or 140 meters, and I think that's highly unlikely. Okay, so let's take a look at an example from scratch that we've never seen before. On a hot day, 6 cars were left in the sun in a car park. The length of time each car was left in the sun was recorded, as well as the temperature inside the car. So first off, we're going to calculate. We're using the GDC for all this. Don't get too concerned. We're going to calculate the mean of the amount of time, which is X. We're going to calculate the mean of the temperature, which is Y. We're going to put all this data here into a scatter plot. We're going to add the mean point to the scatter plot, and then we're going to rough guess, line of best fit, approximate a line, and then we're going to use that line to understand what's happening in the gaps between these data. Okay, so here's how we do that. I got my calculator out here, and again, I don't think you should have to struggle to get the data in there. We've done spreadsheets lots, but always check the last one. F is the 6th letter of the alphabet. F is the 6th one's there. It's all good. Calculator, first thing I do is I'm going to do a 2 variable statistics, because that's where I'm going to find tons of useful information. So 2 variable stats. X was the amount of time. Temperature was the dependent variable. And now I can go ahead and find that information that I seek. So the average, there it is, the average amount of time was 30 minutes, and the average temperature was 38 degrees Celsius. So that's already good. By the way, R value, very high, certainly above that safe zone of about 0.85. So a line of best fit is an appropriate tool to use to understand the relationship between the amount of time a car's been parked in the sun and its temperature. So I'm going to go here, get a new screen. Now you may want to hit stop a few times to check out what's going on here. You can see my spreadsheet still there. I'm going to go to a graph entry, and I'm going to ask for a scatter plot. So it's actually just like plotting in the points from a table of values. You put the names from the column headers in, and it pops it on. I'm going to make some adjustments to my window so I can center that pretty good. Move that label away. And now you can see. I'm going to advance this over to the end, I think somewhere. Okay, and now you can see here what I've done is I've added the mean point, and it's through that point that I'm going to try and wedge a straight line that seems to capture the essence or the trend of that data, but it must go through that point, 3038. Now I want you to notice that 3038 is not actually one of the data points, it's the average, and we've seen from chapter 3 that the average needn't be an actual member of the data set. So we've done those first things there, right? So now what we're going to do is on top of that, we're going to simply estimate a line of best fit like that. Now, usually in test and exam questions, you're going to be given a blank set of axes that you can draw upon, and given a ruler, and you can actually locate the mean point, and then superimpose a line. And if you're near enough to accurate, you're given the benefit of the doubt. The more important is how you use this line going forward. That's what we're going to do now. We're going to use this line to measure what's happening in the spaces between all of these data over here. For example, they said predict the temperature of the car. So temperature of the car was Y. So we're trying to find an unknown Y value for a known X value of 35. So I went to where X was 35. I went up to the line and went back, and I read off the corresponding value over there. It looks to be about 40. Now this scale is not easy for you to read. I had to stop and actually count the ticks on the axes, but it would be easier in a test where the Cartesian plane is given, and I came up with approximately 40 degrees. Then it said how long would it take to reach 55 degrees. Now we're getting into extrapolation country here. Now I can't say whether or not this is a reliable thing to do, because maybe it wasn't even 55 degrees outside. I mean, why would a car reach 55 degrees if it wasn't even that warm outside? I suppose there's some sort of greenhouse effect inside a car, but I'm not certain that this is reliable. But I'll go ahead and I'll try. And I'm going to make some adjustments here. You can see that my value here just changed to make it all fit. And this is clearly an extrapolation because we're outside the data field right there. And when I go ahead and measure it, I come up with approximately, I think it was, let's go back here again. Yeah, I came up with approximately, here's 55 degrees, and I came down here to measure it the other way, and I came up with about 75 minutes. Reliable, it's, you have to make a case for it. So we're in 6E now. We've done B, C, and D. We're into E. Some questions here. You're going to be asked to find the mean points get a diagram on your GDC, transfer it over to paper, and then try and make some predictions about this stuff. So not a lot of questions, only 2 questions to do here, but they're valuable questions and they'll take you through all the steps that you need. Okay, good luck.